Hello, I'm Michal Rutkowski. I work at Yammer as a services engineer. Sorry, I just need to get acquainted with the tools. Okay, so this is the rough outline of what we're going to talk about. I will briefly tell you about Yammer for those who don't know. Then I will explain what we wanted to change and why. Then how we rolled out Cassandra and what problems we encountered. And finally, I will conclude by talking of what we've learned and what worked well for us on that project. So, as you can see, Yammer is an enterprise social network whose goal is to facilitate better and faster communication within an organization. Here are two screenshots. One shows a view of Yammer, which probably looks familiar, quite like Facebook, I guess. It shows a group view. We are looking at one of the groups in Yammer where teams collaborate. And the right-hand side screenshot is the inbox, which covers the conversations which the user follows, which are addressed to them, or the user was mentioned in. But both these are considered to be something we call the message feed. There are quite a few other message feeds. And I would say that Yammer is all about messaging, and the concept of a message feed is quite central to the product. But the talk will be about extracting this inbox message feed to a separate service and why we did it and how we approached it. So this is a quite outdated diagram of service dependencies in Yammer, but that's the best I could find. As you can see in the center, there's this purple box called work feed. That's our Ruby on Rails mono app. It's a bit of a legacy. And the green things around it are Dropwizard Java-based services. For those, I don't know, how many people know what Dropwizard is? Okay, quite a few. Well, Dropwizard is not so much a framework, it's more like a glue which brings together several convenient-to-use libraries, and which allows it's open source, and it allows us to quickly develop services. It kind of removes the boilerplate. Anyway, so the problem we are facing, we are trying to extract features from workfeed into separate services so we can iterate on them independently. But it's a bit of a legacy to work with that. And you can see as well that this is pretty complex. So this requires us to have quite a bit of decent operational tooling. So we obviously have we have continuous integration to ship with confidence. We have a tool for deployment. It's also a Dropwizard service, which we built. We have quite a bit of analytics. We even built a system for querying multiple databases, and we have a whole team devoted to analyzing data scientists, I guess. And Dropwizard comes with a library called metrics, which makes it very easy to capture and measure behavior of the service or characteristics of the data which it processes. And it's also an open source project. We piped it to Kafka, and there it's being transformed a bit, and it's pushed to a tool, like a third-party tool called Waitfront. It allows us to visualize and create quite complex queries, actually, both for past behavior analysis as well as kind of on-call real-time monitoring of the system. So this is more or less real-time. I think it updates in 10-second intervals. And we, of course, we use log aggregation, the Logstash and Kibana. So just to give you an example, this is how the screen for our deployment tool. Royal Mail is the name of the service. It was developed in London. It dealt with inbox. Kind of sound like a sensible name. You can create a package, you can deploy it to a different environment, you can see the recent history, you can also see a more wider view of what's happening in the org in terms of deployments. And here to give you an example of our monitoring, this is reading the inbox graph. You can see latency and you can see frequency. There's this one graph which is a bit out of line. It turned out this was a faulty node. Basically, we had RAM errors, so it was getting a bit out of sync, and it also affected our P99 latency of serving the inbox. But this is the kind of things we use. So, more to the point. So, what did we want to change and why in this project? So, we wanted to extract the inbox feature from an existing service. It was already extracted out of the Mono app because it powered all the messaging feeds. And we wanted to be able to iterate faster on the inbox itself. We didn't want to be constrained by the kind of common denominator of feeds. And we also were facing a different problem. We were working across DC. We needed this for data recovery. And our existing database based on Berkeley DB was in process. It was expensive to scale. It had a bad support story. And it didn't particularly well work with cross-DC setup. So there was like a product motivation, but we also had an infrastructural motivation for this project. So to give you an overview of, like, from that more complex diagram, that's roughly how our message pipeline looks like. So we have the Rails mono app, which is powered mostly by the Postgres, but we also have an async job to update, to talk to the drop wizard service, which powers our messaging feeds. It serves as a bit as like an index service, if you like, for the database there, because the range queries on this SQL database are too expensive for us. So just to give you an overview, user posts a message, the app does some logic to decide if they are allowed, etc., etc. It's stored in the database, and then a task is put on Rabbit. A worker picks it up, decides who it's to be delivered to, and then sends off to the drop wizard service, which updates their database. And when a user wants to read an inbox, it asks the Rails app. That Rails app delegates to the drop wizard service to tell us what's the content of that user's inbox, what threads are in it, and then it hydrates it with the contents of the messages stored in the Postgres DB, which is actually fronted with memcache. Yeah, and the result is returned to the user. So what part of that system we wanted to change and how? Well, again, the view. So we wanted to change that backend. And yeah, so sorry, it was a quick jump. So we wanted to break down that drop wizard service, and this is what I'm going to be actually talking about. We didn't want to break it into two pieces, and we wanted to remove the BDB backend. So now we came up with a rather complex diagram. I would say it's probably too complex, but it's a stepping stone in our overall overhauling of posting architecture. But basically what happens here is the old stuff happens, and once it happens, we spin off a second task to update our new service, basically. It would probably be, like long-term, we want it to be more a pub-sub model. And actually, I'm going to talk about this component of the picture today. So a drop wizard service backed by a Cassandra. So, okay, we know why we wanted to do it and how, roughly, but a few words about our methodology. So we wanted to capture our API and the semantics of that API as early on in integration tests, so that we kind of knew that what we are delivering actually satisfies the requirements. We also wanted to use production traffic for both capacity planning and load testing. To that end, pretty early on, we did a shadow deploy of the service, and we used double dispatch for both writes and reads, just to see how it performed, etc. We migrated the data early so that it worked on a realistic data set, and we are running verification tasks to pick up any data inconsistencies between the two databases, because, as I said, it was also a legacy integration, so we're bound to miss things, and we wanted to detect that. And we kind of also assumed we're going to make mistakes, both in data modeling, so we'll come up with bad design, but we'll also miss use cases, something I mentioned just before. So we wanted to make the backfill or migration task from the old to the new database as cheap as possible and easy to do effectively. So that if needed, we could do it a few times a day effectively. So to give you some context, what we knew is that Inbox is very read-heavy. It receives about 500 million read queries a day. It's not so write-heavy. 1/10 of that is actually writes to individual inboxes. But what we have is we have massive spikes. So a single message sometimes can fan out to 300,000 inboxes. And we do fan out on write. So we needed a technology that will be good for reads, but could also provide like real-time delivery in the face of these massive fan-outs. We wanted the writes to be actually also pretty fast. So the first step was to choose the database to back our new service. And we considered React and Cassandra. We actually have run React in Yammer. We were running React in Yammer already, but we weren't sure if it will be a good fit for our data model. But both of them are sharded and replicated, so that provides us horizontal scaling. So it addresses the expensive to scale aspect. And it's replicated, so it should be highly available. It both work well across DCs and have a support story, something which is important for us. We have paying customers, and we don't necessarily have the in-house expertise. So in the end, we chose Cassandra because we did not want to be forced to do a read, modify, write on a message delivery. Basically, by that I mean With React, unless we went to a super complex, difficult to understand in terms of performance data model, we would have to read the whole inbox, update it, and write it back. Now that could provide network saturation problems, but it was also bad from performance perspective, and especially if the inbox was contended, because there were multiple writes to it at the same time. This kind of optimistic transaction system setup wasn't great for us. So that's why we went with Cassandra, because it allowed us to update exactly what we wanted without reading the inbox, which would give us like very fast writes. So the second phase was to get something working out. So we provisioned the hardware. We came up with a decent RESTful API. By decent, I mean something which captured probably 80–90% of the use cases. The rest we discovered in the due process. And we built tests around that API, and we set up a build process that runs those tests and actually starts the service and hits Cassandra. This is a Java service. Cassandra is in Java, so we used Maven, basically. But it takes 2 minutes to run the whole suite of, I think, 200 tests. And we started implementing against it, basically. So just to go deeper into the design of like the principles by which the inbox works. So it stores, as I said before, it stores the threads addressed and watched by the user. And those threads, when we view them, are ordered by most recently replied to. So we want the most recently updated threads to be at the top of the inbox. But the thread contents, as I've said before, isn't actually stored in the service. The hydration happens outside. This is like an index, basically. So on a message post, we would deliver the message to every inbox. And this effectively amounts to updating the last message ID so that we can maintain the ordering and some little pieces of metadata. And on read, we would paginate. We would just read the most recent threads, let's say the most recent 20 threads. And quite often, and we would filter, mostly by read unread. There are some other cases, but they don't matter that much. So we came up with the first design. It was pretty simple. We had a table for inboxes. It was partitioned by inbox ID. It was primary keyed by inbox ID, last message ID. For those not familiar with Cassandra, if you have stuff in a primary key, basically data is ordered by your primary key. So that effectively meant that data is ordered from the most recent to less recent stuff. And we use secondary indices for filtering. The filters were of small, they were like 3 values for a filter at most, so they were a good fit. And we had a thread table because we needed to maintain some metadata for updating the inbox table, like who got updates in the past, and what's the last message, because in order to update that table, we need to know what was in it before, so we had to check it by thread. And yeah, this was partitioned by thread ID, and it used the set CRDT, so kind of eventually consistent data structure provided by Cassandra, which was very convenient. So it was great. Tests were passing. It fitted perfectly with our usage patterns, and was self-healing in the presence of out-of-order deliveries or system partitions. It was also idempotent, more or less. So except that, it brought our migration task to a halt. It just wasn't working with our migration traffic. So what went wrong? Well, we discovered that the secondary indices are slow, as hell, actually. CRDTs are okay for small and infrequently updated data sets, but not something like our subscription lists, which we try to keep very consistent. And secondly, the cost of our conveniently stored data was the heavy reliance of deletes, because the message ID, which was in the primary key, could not be modified. It had to be deleted and reinserted. So that's a no-no in Cassandra world. So what do we do now? Well, we actually expected this kind of thing, because we're only just learning Cassandra. Nobody of us from our team used Cassandra before. And we actually wanted to push something out as quickly as possible so we could get realistic data to benchmark our solutions. But what was important is that our API was already established, and we had the semantics of that API well captured in tests. And we had this migration task available. So we could use our metrics, our tests, and the migration to quickly iterate on implementation. So this was a bit of a setback, but it wasn't the end of the world. So we came up with a second design, which was a bit dramatically different. We forgot all the Cassandra extras and designed around what it's good at. And in order to come up with this design, we kind of went deeper into our product requirements or feature requirements and tried to leverage that to make sure that our design actually works. And we use analytics, metrics, etc. So we discovered that we do not need to keep all the data. We just need to keep recent stuff because content is searchable otherwise. And for instance, 5,000 entries only take 75 kilobytes, so it's relatively little, and it covers 4 years for an active user. So if we kept on that, we would be pretty much doing everything we need to, or more, and we will be able to do what I will explain in the next slide. And then importantly, since this is an index which basically tries to show you what content is available and in what order, we actually don't have to be that exact about what data we store. So let me explain. So just to give you an example what we came up with, we decided we'll partition still by inbox ID. This was important because it meant that hot and less hot networks in Yammer would be evenly distributed, so there would be no hotspots. But this time we decided to partition by inbox ID and thread ID, and made the last message ID that as our mutable metadata stored in the inbox. And the secondary table basically dropped, that thread table basically dropped the use of CRDTs. We just used it as a hand-rolled, manually maintained secondary index. So this was clearly going to be mutation heavy. So we decided to use leveled compaction. I don't know, how many people are familiar with compaction in Cassandra? Okay. So Cassandra uses, has a 2 tiers to it. It has a append-only log. That's why it's very fast at writing. But then that log is consumed and materialized in something which is called an SS table, so a sorted table, I guess. And that's only then it's usable for reading. And these tables are immutable. So when there's, let's say you have an entry in that table and you mutate it, what effectively will happen is that a new table will be created with an override. So a query for a value will have to go through all the SS tables which contain it and take the most recent one. And typically Cassandra uses called size-tiered compaction, so where 2 SS tables become of similar size, or 4, I don't remember the exact details. They're compacted into 1. So this way, next time you query that SS table, you only have to read 1, not 4. But level compaction is a bit different. It uses 12 levels and ensures that at most you have to consult 12 SS tables, but expected number of SS tables is around 1. So that makes it, at the cost of constant low I/O, it makes reads much faster. Was that clear? Okay. Sorry. So we knew that there will be race conditions on updates, but that's what I meant by not being exact. On active threads, it doesn't matter. We just order and filter. So if 2 threads are competing for the top position, or they have like the last message ID is not the actually last message ID, but the one before, it doesn't matter because we still can serve relevant content. And on less active ones, races will be negligible, and users will correct it effectively. And especially the second one was a bit of a hypothesis, which we had to verify, but it proved correct. There are no complaints about ordering in an inbox. And on read, we read the whole inbox now. Not just the top 20 threads, but we have to read everything. We sort it and filter. But data is small, so it's actually okay. Even better, because of how we represent threads, where the thread ID is actually the ID of the first message in that thread. This data is semi-sorted, so sorting of 5,000 entries isn't particularly expensive. And we trim excess data to make sure that inbox stays in check. So we read, I think, 15,000 records, trim it to 5,000 after it exceeded 5.5. So we don't trim every time, but give ourselves a bit of a buffer. So this time, we got to production and passed the migration step. It was even working in the shadow mode, module some data inconsistencies from use cases which I mentioned. But the read performance was very varied and below our expectations. So what now? So again, usage metrics, zoom in even further, get more detail out of it. So out of the 500,000 queries we see every day, 90% are for an unread count, actually. It's important to visualization in Yammer. Because the reason that is the case is because we heavily rely on real-time delivery through command D. So actually, the actual load of an inbox happens relatively rarely, but we refer to the unread count quite often. And furthermore, the number of unread messages is usually very small. So users have, 95% of the users have less than 100 unread messages. 1% has 1,000 and more. So reading 5,000 entries was totally excessive and exposed us to much I/O. So we decided to materialize that query and basically maintain a second table for those lookups. It was a separate table with just unread stuff, so it was trivial to query. We just query select 1,000 entries from that table, and we return the count. So where did it get us? So our rate latency is less than 100 milliseconds for regular messages. I mean, this is not like this. This is whole service latency, if you like. And it's less than 10 seconds for massive spiky announcements, which is okay. The announcements don't have to be that real time, but overall system is pretty robust in terms of writes. And read latency is pretty good. Our P99 is 250 milliseconds. 999 is less than 500 milliseconds. That's for the whole inbox. Again, that happens relatively rarely, so having a bit of a spinner for that is okay. And the critical query is less than 30 milliseconds. So it gives us what we want. So yeah, we shipped. And yeah, I should ask you for questions now. But actually, not so fast. Because 3 months later, on my first day of my summer holiday, Yammer is down. The site is down, our service is on fire, and free Cassandra nodes are on fire. I've spent a few hours on a call with San Jose and San Francisco from Warsaw when my family expected me to be with them. So that wasn't fun. So what went wrong? So first of all, it turns out that having an HA service, we had 3 nodes with a load balancer, netscaler, all that cool stuff, and a highly available database doesn't make your site HA. The root is it's never one thing, but the root of it was a massive inbox, which was receiving tons of updates, but was never read. This meant it was never trimmed. So it grew to like 100,000 of entries, effectively. Now, level compaction didn't like it, because level compaction has to rewrite an inbox on every compaction. So each write would effectively trigger a compaction. That compaction had to deal with loads and loads of data. So our trimming strategy, so what were the deeper problems? So our trimming strategy didn't account for overgrowing inboxes' impact on compaction. We just, again, new technology, we didn't fully understand it. So yeah, we overlooked it. But there were a more fundamental problem. Our main app didn't have circuit breakers, so when the service was slow and to respond, it was waiting for quite a long time, and the thread pool was exhausted, so we couldn't serve traffic. The service itself didn't control its resources, as in, when a request was running long, it would run for however long it had to. Maybe 10 seconds, I think that's how much by default Cassandra. It's probably about 10, 20 seconds because I think it gives a second try, the datasex driver. So yeah, so it was easy with 20 seconds per request. It was easy to exhaust its thread pools and backup requests in the request queues. So what did we do to fix it? So first of all, we added probabilistic and asynchronous trimming on delivery. This was to deal with those inboxes which brought us down initially. But we also went a bit further and we decided to keep tombstones for shorter, so that actually even if we, because after the delete, the tombstone stays until it expires. So even though we delete data, it will still have an impact on compaction until it's collected. You need to keep a tombstone because if you delete, and the data hasn't been replicated to all nodes, it will resurrect. So tombstone is like a marker that this has been deleted, and you keep it until you make sure that your delete has been propagated everywhere. And the second bit, so the repair job, this is something you run independently across the whole cluster. This makes sure that all the writes were propagated. This buys you time on actual write, because you can just write to a quorum. And then you run a repair job, which makes sure that this write has been propagated to everybody. And so we decreased the grace period, so tombstones stayed for shorter, so they had lower impact. And we had more frequent repairs for that reason, because you need to repair more frequently when your tombstone lives. So if your tombstone lives for 10 days, you should repair the whole cluster every 8 days, so that your tombstone doesn't go away before you've propagated the delete. So we shortened that period to favor smaller but more frequent repairs. This kind of made our trimming also much more effective. We also looked at the service, and we used something which I guess is referred to as a bulkhead pattern. So it was not, it's effectively timeouts, but it's service side. So basically the service controls how much it runs the operation. So this way, for each logical operation, say deliver a message, read and read count, read the inbox, we allocated a separate thread pool for that operation, and we guarded it with a timeout, so that if that operation is running for too long, we basically cancel it, regardless of the timeout on the client. And on the application, we roll out circuit breakers. So I will go explain this in a bit more detail. So is this fixed now? Is this the end of all of that? Well, more or less. We still have some problems with running repairs successfully all the time. And we also have seen things like a single bad node. By bad, I don't mean dead, because that's relatively easy. I mean slow. One which thinks it's OK, but it isn't. Taking down the whole cluster. We think it's basically because it's basically replay of what we saw with our system. Basically, the node responds, so the other nodes wait for it, but it responds so slowly that they basically exhaust their resources. But it's not so trivial to tweak, and it's actually not very easy to reproduce, because it theoretically shouldn't happen, but we saw it happen. So we have an ongoing task to inject latency and reproduce it to actually figure out how to solve it. But what's important is that even if we haven't solved all the problems with the backend, a problem with Cassandra or the service doesn't take the site down, because it has decent kind of failure isolation. And the bulkheading pattern means that only the users whose data lies on the problematic nodes are actually affected. So what do I mean by this, and how this is achieved? Well, let's say we have a 10-node cluster, and 3 nodes, for some reason, are in a bad state. So that roughly accounts for 30% of the data. So in the past, that would effectively mean, because of faults in the service design, that would mean that still all users would be affected. Now we actually observe that if that happens, and that can happen, that 3 nodes for some reason, bad memory, etc. We run our own DC, so we deal with that. We have only 30% of the users affected. So the ones whose data is on good nodes don't see it, because they are, thanks to the bulkhead, they're isolated. And the bulkhead works the following way. So we know what's our peak traffic. We know what's the worst case latency we are willing to accept. So we size the thread pool in such a way that we have enough threads during the worst latency. So even if some requests are timing out, it doesn't exhaust the thread pool, and there are threads available for the other requests, roughly speaking. So what worked well for us with this rollout? Our methodology proved to be quite successful, I guess. So we had the integration test, which allowed us to ship to prod with confidence. We had data model modifications, which we took about an hour or 2 hours to implement, and then 2.5 hours later, it was in production. So that's pretty good, I guess. The shuttle deploy and double dispatch gave us great feedback on design from the actual traffics. Migration gave us peak performance feedback. And existing metrics and analytics were very informative, gave us loads of information to inform our design choices. And I think that was really important. The easy-to-run migration really allowed us to move from one model to another very quickly, and this was not a problem, effectively. Instead of trying to avoid problems, we kind of allowed ourselves to quickly deal with them. I guess this was the trade-off we did, and that proved pretty successful. What we've learned, however, is that even for a big organization, Yammer is, I guess, now 350, 400 people, probably about 100 engineers. Introducing a new technology has a high cost. getting a working model in production took only 3 months. Even though the actual project lasted a bit longer, but this was due to dealing with legacy integration. But getting the technology out was relatively quick. But what takes a lot of time, and you have to commit your resources to it if you're a serious organization, is ironing out the operations. And that will take at least a year. Because you need to understand your system in much more deeper detail than just to roll out a feature. And if like Yammer, you have an SLA to which you commit, you really need to have a much deeper understanding than just to roll out your feature. You'll have a lot of firefighting and fixing, and you also have to train people, because even if you do it as we did it in a cross-functional team, there was a person from every bit of the stack, including operations engineer, involved. Well, we don't have too many. We have all the necessary resources. Then you have to propagate the knowledge across small operations engineers, small services people, etc., etc. And that takes time as well. And support helps. And they did help. Data stacks support helped us a lot. But above still holds. So if you don't have support, you will be even in a worse situation. I guess it kind of echoes the stuff mentioned by a guy who gave a talk today from Etsy, that it's try to solve cool problems using boring technology rather than introduce unnecessarily. In this case, we had a reason, but any technology introduced to your org will effectively mean this, I would argue. Yeah, so thank you. And this time it's for real, so any questions?